Hello everyone. Today we'll be looking at the car auction data set where we have the pricing of the cars and the corresponding Excel file is shared with you. As you can see in this row we have the index number for the car, whether there is airbag or not for the car, as an additional feature, whether there is leather trim as opposed to clothing trim, and then tinting of windscreen is existing or not in the car, and the amount of miles for the corresponding car, the age of the car, and the price of the car as it was sold in 2007. And as you can see, the indexing is actually depending on the year, and there's a corresponding number assigned, and we would like to be able to analyze this type of data set. Now, what makes a difference in this data set, as you can see here, the airbag is whether there is yes or no, which is different than the data sets that we dealt with before, because we either had 0 or 1 or 1 through 5 as the numerics here, but this time we are dealing with qualitative information. And we'll be learning how to analyze such a data set as a part of the lecture today. And then we'll be looking at what's so-called backward elimination by using StatProGo. Now let's continue with the lecture here. As you can see, if you look at the graph price versus age, you have a certain trend here, age versus price. It doesn't have a linear trend, meaning it is not a straight line. As you can see, it's sort of a curved fit on this part. It's exactly the same for price versus mileage. So if you take a look at this data, it is not necessarily a straight line. It is curving just like this. It is not a straight line. Therefore, we would like to be able to see what type of fit we can have and as a model. And here you can also see that we have 1, 2, 3, 4, 5 performance measures or variables that can be related to the price. Now, as a part of the pivotables, as a pivot table, we can actually look at the airbag option, whether there's airbag or not, and we can take a look at the average of miles, average of age, average of price corresponding to that, and we can see the grand totals accordingly. So as you can see, if there is no airbag, the average price is lower than the ones that we have, and you can see the difference between them in terms of average of miles. But again, this gives us an idea about the importance of airbag, but it doesn't specifically tell us the difference between them, because here average of miles is high for no and it is less for yes, while the average price is increasing. So a mileage and airbag, these two, we don't know how they relate to this price. They are high. For example, the mileage is high, which could be impacting the average price directly. Therefore, additional airbag may not be causing that much additional pricing, because average of miles is less here. It's about 10,000 miles less when you compare to the additional feature. Therefore, we need to have all these incorporated in the model to be able to see the big picture of how these are impacting the price of the car. Now, moving on, we can actually convert airbag information into zeros and ones. Now, if you take a look at here, if the car auction Excel sheet that we have here and the corresponding cell B3 is yes, then it's going to be signaled as 1. This means in this Excel spreadsheet, if B3 is equal to yes, meaning there is airbag in the car, it's going to be 1. Otherwise, it's going to be 0. So let's go to car auctions, and as you can see, B3 is no, Therefore, the corresponding number should be 0 here. If you look at, for example, B6, which is 1, under car auction sales 1, it is yes. So this is how it works with 0 and 1, whether it is no or yes. And that's how we can actually create this column in that fashion. It's exactly the same for leather trim. If there's leather trim, then it's going to be signaled as 1 here. If there is no leather trim, then it's going to be 0. And same for tint. If there's tinting in the car, then it's going to be 1. Otherwise, it's going to be 0. And it's really easy to come up with this column, because if you just type this information in, you can just click on this plus sign and drag it down, or the corner part, right, left. If you click on the left part of the mouse, and if you drag it down, you'll get to see that the data will be generated for this entire formation. And if you go all the way down, how many data points we have? About 125 data points, or 124 data points that we have. So this is how we can convert a qualitative data into quantitative data in this fashion. And one thing that I mentioned that I'll be explaining later is also residuals, which is something that we can attain by using StatProGo, which is actually telling us information about whether the pricing of the cars are under or over the expected price. Now, if you take a look at residuals versus age, here you can see that age is increasing starting with 1 up to 5. And we have all the data in between 1 through 5 with the corresponding pricing. And we get to see the residuals of each car. Now that information is here, which is attained by using StatProGo again, after coming up with this multiple regression. And I'm going to show here that I'm going to explain residuals versus age part. Now, if we have 1-year-old cars, as you can see, the cars are underpriced. This is what it's meaning on the residuals part. If you take a look at ages between 1 and about 5, close to 5, all the data points are above the x-axis here, the input axis. Therefore, the cars are a bit overpriced than usual in this setting. And it's exactly the same for 5-year-old car as 1-year-old car. Majority of the cars are underpriced based on their age when they are 5 years old. Therefore, we get to see that the model that we have, or the residuals versus age, tells us that there is overpriced and underpriced cars depending on the period of time. And as you can see, residuals versus mileage is exactly the same here. For those with less than 25k mileage, you get to see that they're underpriced between about 25 and 100. Or yes, between 25 and 100, they're a bit overpriced. And then above 100, they're underpriced based on the data that we are seeing here. Now, as a part of this, what we covered in the past is coming up with a regression model. As you'll recall, we have air, leather trim, tint, miles, and age in this case. So all you need to do is, by using add-ins, StatProGo, go for regression analysis, multiple regression, and include air, these columns right here, air, leather trim, tint, miles, and age here as the input variables, and our corresponding output is the predicted value. Now what you would see here is that we have the constant, which is $51,118 about, and every time There's airbag, it's going to be $606 additional dollars. Leather trim is about $867. Tint is about $222. And every time the mile increases, it's decreasing by $225, and age is increasing by $937. Now you need to be critical and criticizing this data, because this tells us without any of these, the value of the car is about $51,118, which seems to be not really realistic. Therefore, we should be able to come up with a better model, and residuals graph here tells us that this is not really a good model for what we have, even though we have adjusted R-square as 92.9%. So we need to look at the residuals graph to be able to understand whether the model that we came up with here is a good fit to the data or not. Now, another new thing that we'll be dealing with today is what's so-called quadratic regression. Now, quadratic means we are actually going to increase the number of unknowns. For example, here we have miles. Now, miles can have square impact. Therefore, here we are taking square of each mile. Therefore, we come up with this new column G, and we call it miles 2 because we will square this column miles here. Each value under this column E would be squared under column G. Here you can see this value is squared, E3 square and E4 square, and so on and so forth. Now, we also incorporate H square. So all the H values here will be squared. As you can see, we have F3 square. Now this is F4 square, F5 square, and so on and so forth. 5 square becomes 25, 1 square is 1, 1 square is 1, 3.4 square is 11.6, and so on and so forth. Now, why do we do this? If we increase the number of variables and the degree of variables, which is here, as you can see, miles is squared, age is squared, and the other variables are not squared, we have a better approximation of the model, which is about 97.4%. Now, here you might say, well, why don't we do this for all the other variables? Because we will have a limitation. About 20 columns can be only incorporated in a StatProGo solution. It cannot be more than 20 variables. And mile square might be one of the important factors, as well as H square can be one of the important factors. Now, after adding columns G and H to the original one that we have here, or after coming up with the numerical part, we add columns G and H. Now we also include that here, miles 2 and H2, these two new columns. And obviously we actually come up with this model again from Erin's StatProGo regression analysis and multiple. So this time we have 1, here 2, 3, 4, 5, 6, 7. And the number of columns we have 1, 2, 3, 4, 5, 6, 7, as you can see. And this time we have mile square, H square. As you will recall, after coming up with this adjusted R square, we need to check on that 97.4%, which is better than 92.9%, the one that we had. Therefore, adding these two, mile square and H square, appear to add value to the new model, right? We have a better adjusted R square, which is what we care about. But we also need to be careful about the corresponding p-values, as I mentioned before. Now here you can see we have miles, I'm going to highlight that, and H square. These are, and also actually we have H. These are 3 high p-values. Now you will say now, or you might say, okay, how are we going to handle this? How are we going to eliminate all these? The way to do that is simply called backward elimination. Now, in this part, we can actually eliminate some of these parts and come up with a better model by checking on the adjusted R-square. How do we do that? When I look at here, I see that H-square has the highest p-value. Therefore, we can take out H-square because it doesn't have too much impact on the corresponding model. And I'm going to move on to backwards tab now to be able to explain you that part. Now, as you can see here, we don't have H-square anymore here. We have all other 6 variables, but H-square is missing. And you might say, how are we going to generate that data? It's actually very simple. You can go here. Now, as we edit this, you can simply just click on this column and delete this column. And use add-ins start progo, again, multiple regression, just like we did before. And we will come up with this new model, right? Here we have H-square coming from the previous one. Step 2, we take out the H-square one. Now, what you will see here is a new set of p-values when H2 is eliminated. That's why it is called backward elimination, because we start with the most extensive model. We have 2, 4, 6, 7 variables. Now we take out H2 for step 2 right here, and H-square is not here anymore. We use start progo and come up with this new p-values. Now, as you can see, this value right here, 0.625, is the new highest p-value. In the next step, which is step 3, we take out miles. How do we do that? We go back here. Now we actually delete this column, right? Therefore, and then also use again start progo and come up with the new set of variables. So as you can see, miles right here, this one is taken out here. We don't have it anymore. Even though miles square remains same, we don't have miles anymore. One thing we need to be careful about is miles square is depending on miles. So deleting that might affect miles square. Therefore, you can actually remove this. You can cut this and paste it somewhere else and just use stat progo to be able to analyze the remaining part, which is going to be pretty simple. If there's another variable like miles square, depending on miles, deleting miles would clear up all miles square data, which is not a good idea. So what I mentioned you before, please ignore that and just cut this and then paste it elsewhere, just like here. And then Control V should do that. And you can just simply delete this part, and you can use stat progo to be able to analyze that. As you can see now, you don't see miles square anymore. Make sure to leave a column empty here, because stat progo is going to recognize the area here in that setting. Now, if you keep doing that, every time you improve the model by taking out a variable, you actually get to improve adjusted R-square value. Now we have here, sorry, it's here, 97.37. In step 2, it becomes 97.39. So let's go back here. Not too much improvement from 97.37 to 97.39, but very slight improvement. And then it becomes 97.41. Actually, even though there's slight improvements, we are eliminating the variables that we don't necessarily need in our model. That's something very important for us, because as we clear all the variables by using backward elimination, we end up finding a clean model. a model with the minimum number of variables. We started with 5 and we reduced it to, we started with 7 and we reduced it to 5 variables. Now let's check on the p-values, which is right here. All these values are less than 0.2. As low as they are, as good as it is for the corresponding model. Now, brand new car, $47,201, and it was actually initially $47,318. So this seems to be more realistic, but not too far from the first step of backward elimination. This is very useful in the sense that we have an idea about the pricings of the car, even though these values do not necessarily reflect the reality all the time. So this is something we have to keep in mind. These are approximate values close to what we would like to observe or what we would like to have an idea about. They don't necessarily reflect the perfect outcome. This is something very important we need to keep in mind. I'm skipping explaining all these. The ANOVA stands for analysis of variance, and all these components have meanings, but as we have limited time and as the camp is not requiring too much details of the statistics, we are not getting into the details of these in that sense. And the final model in this case is with all these 5 variables, which comes from step 3 right here under backwards tab. We have air, leather trim, tint, age, and miles square, which is the final model here. And then we have the constant value. Assume we have an airbag, leather trim, and tinting in the car. The car is assumed to be 3 years old with 80,000 miles on the car. The corresponding price is about $39,442. Now, to be able to see whether this is reflecting the reality or not, you could go back to the data and check and see if actually this model, the very last model we have right here, the final model, is reflecting the reality here or not. So that's something I'll leave as an exercise. It could give us an idea about how much the pricing of the car, but it doesn't necessarily reflect the truth, like perfect truth, or sometimes it may not be also close enough, because we are dealing with about 5 variables here, 5 unknowns that impact the price of the car. And this type of model could be used for coming up with, let's say, a car is sold and you would like to see its predicted value under the data set existing, and you can enter the credentials here and see how much it could worth approximately, not necessarily exactly. So I hope you have a good understanding of how we convert qualitative data into quantitative data, and also come up with regression, come up with new columns which are squared values of the existing variables, and use backward elimination to be able to simplify the model we started with and end up finding the best model that we could come up with based on the p-values and adjusted r-square values, and be able to see if we can actually predict the value of a car with certain values under consideration. And thank you for listening, and we'll continue with StatProGo implementations for data analysis and decision making.